As a species, humanity, and also to discuss our collective vision towards a shared future. But what is the future I'm talking about? It is not the future of us as a society, of us as a civilization, but I'm interested in our future as a species, humanity. And I'm interested about our future as a species in the context of our place in the universe. Okay? So for thousands of years, we as a species have asked this fundamental question, are we alone in the universe? And this is the first time in that history of thousands of years of thought, philosophy, science, and modern science, that we have any chance of detecting the possibility of detecting life elsewhere in the universe. The possibility of answering that question we have been asking for thousands of years. But if you ask, what are the requirements for such a future to detect life elsewhere? We always have this concept when we talk about life elsewhere of finding life as on Earth on a planet like Earth. In other words, an Earth twin. Earth as a sun around a sun-like star elsewhere. But there are two requirements for us to detect life on such a planet. First, you need to have such a planet. We need to discover the planet first. And second, you need to have the observational capability to detect the atmosphere of such a planet and then the constituents, the molecular constituents in the atmosphere that could be indicative of life. The reality, as we speak right now, is that we can meet none of those requirements. Today, we don't know of a planet around a sun-like star like Earth. We have thousands of planets that we know of. We have over 6,000 planets, but none that is exactly like Earth. Second, we don't even have the capability, even if we knew of such a planet, we today don't have the capability to detect an atmosphere around such a planet. So should I stop my talk here? So if that were the case, if this is not possible right now, when would it be possible? That timeline is about 20 years from now. We would have potentially the capability. But then what has happened in recent years are a couple of big breakthroughs, which is why I'm here, to share with you the possibility of detecting life in the near future. Okay? So what has happened is that in the last decade, when we look at these exoplanets, by that I mean planets around other stars, we know of thousands of these planets, and we have realized that planets between Earth and Neptune in size dominate the exoplanet population. We don't have any such planet in the solar system. This plot here is just showing you a summary of planets around other stars, and you'll see that between Earth and Neptune in size, there are lots of planets. And this is called the sub-Neptune regime. A number of space-based facilities have detected these planets. Now, this sub-Neptune regime is serving as the new frontier in the search for life. Why is that? Because in the solar system, you have the Earth, and you have Neptune and Uranus, which are ice giants that are roughly four times larger than Earth in size, and nothing in between. Whereas in the exoplanet population, there are thousands of planets in this range, right? The big question to ask is which of these planets could potentially be habitable beyond just Earth-like planets? So I'm going to talk about that. Secondly, so we have thousands of these such planets, so if we can find planets that are habitable, then we have a lot of them to study. The second major advancement that's happening is what is known as atmospheric observations with transit spectroscopy with new facilities. So in this technique, what's happening is that you as an observer is watching the star as the planet is going in front of it. And when that happens, some of the starlight that is coming from that is passing through the planet's atmosphere before reaching you will be absorbed in the planetary atmosphere. Okay? So this is called the transit depth you are seeing here. That's just when the planet is going in front of the star. And that is proportional to the size of the planet or the size of the star squared. In other words, if you can make these observations of transits at different wavelengths, you can see this is known as a transmission spectrum. And this absorption is caused by the molecules in the atmosphere of the planet. Okay? So this was done with the Hubble Space Telescope more than a decade ago. But what's happening now, just in the last couple of years, is that this area of atmospheric spectroscopy of exoplanets is being revolutionized by the largest space telescope that has ever been launched into space, that has ever been built. That's the James Webb Space Telescope. Now you can see already that these are for giant planets, Jupiter-sized planets. There are lots of these observations coming. The wavelength range has increased, the sensitivity has increased, so we are able to make lots of molecular detections in such planets. These are for giant planets we are talking about. So what I told you just now is that we have this new range of targets in the sub-Neptune regime. We could be looking for potential habitability, and we now have the big facility that will allow us to characterize their atmospheres. Let's see what progress we can make when we put those two together. So in the rest of my talk, what I'm going to ask is a very basic question. We have Earth and Neptune in the solar system. We know Neptune is definitely not habitable. We know Earth is inhabited, right? The big question I want to ask is that what are the limits of planetary mass, radius, and temperature that allow for habitability in planets? In other words, can planets be slightly larger, slightly warmer maybe, than Earth and still allow for habitable conditions? If that is the case, then we have just unlocked lots of these habitats that we can look at with our existing facilities. So we made a big theoretical breakthrough in this direction. 5 years ago, we came up with this concept of what is known as Haitian worlds. You may have heard the term. The term is not a Greek word, I promise. It is Haitian, stands for hydrogen and ocean combined. Okay? These are planets with ocean-covered surfaces and thin hydrogen-rich atmospheres, which can allow for habitable conditions in the oceans to allow for oceanic life. This is a new type of planet. We have no concept of such planet in the solar system. But if such planets do exist, it was a theoretical concept, then in principle, this is showing the radius and mass of the planet. The blue region is the region in that mass radius plane where you could have such planets that are potentially habitable. These are ocean planets with hydrogen-rich atmospheres that are potentially habitable. But just based on mass and radius measurements, there are a number of other hypotheses that can also explain the planet's density. Right? You could have a mini Neptune-type planet. You can have a rocky planet with a thick hydrogen-rich atmosphere. It is what is known as a degeneracy problem in physics. There are multiple solutions that can explain the density. And that is where you need atmospheric observations. Another point is that if you take the separation of the planet, that's the distance from the star, there is a wide range in separation space where these planets can be habitable. So the habitable zone for Haitian worlds is much wider than just Earth-like planets. So that was a hypothesis we came up with 5 years ago, and then we decided to test with real observations. So our case study here is of a planet called K218b, which you may have heard of. And this is a sub-Neptune planet. The mass is about 9 Earth masses. The radius is about 2.5 Earth radii. And the important thing is that the planet is at the right distance from its star, such that if there is water on the surface of this planet, it could be in liquid state. So it is a potentially habitable planet and was a Haitian candidate that we predicted. So with the Hubble Space Telescope, with a lot of hours with HST, already 5 years ago, there was a spectrum that was observed, and there was a little blip of a feature, and it was debated whether that feature was due to water vapor or methane. There was a lot of debate at the time. But then the observational breakthrough came with just 14 hours of JWST time that we were awarded, that we looked at this planet. Guess what the spectrum looks like? It's that. It's just 14 hours of JWST time. And JWST observes for thousands of hours every year. Okay? What you're seeing here in this plot is the first detection of carbon-bearing molecules in the atmosphere of a habitable zone planet. This is the first detection of methane in a habitable zone exoplanet. So you can see all these points are with error bars are the data. The solid curves are model fits to the data. We can also see a feature of carbon dioxide in the planet, again, for the first time for a habitable zone exoplanet. And we are also seeing some tentative features. Again, this is not robust at all. Some tentative feature of the possibility of this molecule called dimethyl sulfide. Why is this important? Because dimethyl sulfide is a biomarker on Earth. It's produced almost exclusively by life here on Earth. So if this is true, and this is very preliminary, then we may be looking at a biomarker in an exoplanet. But that's a big maybe. There are lots of questions to answer. But you have to think about it. The very first observations that we make, just 14 hours of time with JWST, gives you data like this. And there are other complications. This is just showing model spectra of various molecules. The complications are the molecule DMS has spectral features within the same bands as methane, so it's very hard to detect these molecules. But the proof of concept is there, that if we stack more and more observations, there is a possibility of detecting it. So I'll summarize all of this by saying that with just these observations, we were able to detect carbon-bearing molecules. We were able to not detect some other molecules like ammonia and carbon monoxide and so on. And that combination told us that it is very likely that this planet is actually a habitable Haitian world. And then the search is on for the biomarker in such a planet. So this discovery, this was done a few years ago, already started a new era in exoplanetary science. For the first time, we're actually having observations of such planets and trying to understand what those observations mean. So this is transforming the study of habitability and the search for life elsewhere. But is there other evidence for these biomarkers we're talking about? So if you make a prediction of what the dimethyl sulfide and other molecules like dimethyl disulfide, also a biomarker, would look like, this is what they would look like in the mid-infrared, which we hadn't observed at that point. So then we said, let's go ahead and look in the mid-infrared with another instrument, which we also had time on JWST for. And that's the news that you may have heard last year. This is the first spectrum of a habitable zone exoplanet in the mid-infrared. And we also see some tentative features of this molecule, dimethyl sulfide. But again, we have to be careful because there could be overlapping features with other molecules. So what you're witnessing in real time is history being made of the very first observations. These are the very first insights we're having of a planet that is 124 light years away. We are talking about hundreds of trillions of miles away. And we're able to pick the atmospheric composition of this planet and potentially biomarkers. So there is independent lines of evidence. These are, again, very tentative. We are talking about a 2-3 sigma level detection significance at this point. And there are lots of open questions, as you can imagine. With any breakthrough science, there will be lots of questions. Is the signal actually real? Because this is very tentative. Is the signal uniquely identified to a biomarker, to DMS or some other biomarker? And is that uniquely from life? All these questions are being worked upon by various groups around the world. But then there are also benchmarks in the sense that the same instrument setup, the same modeling strategy has been used for giant planets, bigger planets around other stars, and the inferences are at the same level of significance, 2 or 3 sigma significances. So which means that if we have to look at systematics and all sorts of unknowns in these data sets, those also have to apply to all the other data sets. So we have these benchmarks that we work with so we can do robust science like this. So the summary in all of this is that there is evidence that we are seeing tentative features of molecules that could be potential biomarkers. And if they turn out to be true, then we are seeing a major shift in our understanding and in our search for life elsewhere. But then you want to ask the question, is K218b unique? Did we get lucky once? The answer, as you can imagine, is no. There was another planet, TOI 270d, that was also observed in the last 2 years, and you can see the similarities between these two spectra. Phenomenal, again, with just order 10 to 14 hours of JWST time. So did we get lucky twice? The answer again is no, right? So these were theoretical predictions before JWST flew, and these are actual observations of 3 planets that I'm showing you here. All the 3 planets were predicted to be candidate Haitian planets. And you can see in all these cases, we are seeing strong methane absorption. And in all these cases, we are seeing excess absorption. That's what this X is. Excess absorption beyond what we can just explain with methane. These are all tentative, about 3, 4 sigma, 2, 3 sigma level significances. But the point is, we are seeing tentative evidence for absorption we can't account for with normal molecules. So either we are seeing some exotic chemistry that we don't understand in the solar system, or we are seeing signs of life. And that's crazy if you think of it. Because 5 years ago, I worked in this field for nearly 15-ish years, and even I wouldn't have predicted that this is where we would be in 2026. Okay? So this is a remarkable celebration of us as a species and our technological capability to look at planets that are trillions of light years away, trillions of miles away, and being able to detect these molecules. So 3 fundamental advancements I'll leave you with. We have made the first contact with potential habitable planets elsewhere. Observationally, not theoretically, observationally. And we are seeing this unique congruence between theoretical predictions and observations that are going and confirming them. That's a prized possession in astrophysics. Okay? And regardless of whether the interpretation of habitability and life, we are seeing a new class of temperate habitable planets that are opening a rich area of planetary science and astrophysics as we speak. Okay? So this is the revolution we are talking about. So the promise of this decade is that it will serve as a launch pad in the search for life. So for thousands of years, we have been asking the question if there is life elsewhere. We have been theorizing possibility of habitability and life elsewhere. But for the first time in the history of our species, we actually have data and then we are interpreting those data sets, and that could lead to the possibility of detecting life. But even if these biosignatures are not confirmed, even if these planets don't have life, what we have demonstrated as a species, that we have entered the era where we have the technological capability to detect life if it does exist on these planets. And that is huge. So what is coming is, so you've already seen results with the James Webb Space Telescope, and relevant to here at Chile, there is the extremely large telescope coming very soon from ground. And that is what is going to take us to the next big breakthroughs in the search for life. That's happening right here. So it is our collective responsibility to protect our skies and make these big breakthroughs to establish our own place in the universe. So we have the observational facilities coming up. We have the targets that are present already that we know of to look at. So we started with this notion of finding an Earth twin and a life on Earth twin. So in my mind, that's not a question of whether we'll actually find life. Because what I'm looking forward to is our future, not just trying to understand the sky as an astrophysical background with astrophysical objects. I want to understand our sky as our future. I want to understand ourselves as the future of life in the universe. Do you see what I mean? We, as a species, have always looked at the sky and thought we are unique. But for the first time, if we detect these molecules, if we establish the presence of life elsewhere, we would be asking ourselves the question, how do we compare with life elsewhere in the universe? Right? So that is the context, our future as life in the universe. So in my mind, as I said, the question is not whether we will detect life, because we have the targets and we have the capability to detect life if it is actually there. The bigger question in my mind is that are we as a society, are we as a civilization, are we as a species prepared to find life elsewhere as we don't know it? In other words, do we have the capability to interpret signs of life elsewhere? We surely have the capability to detect them, but are we able to interpret them? Thank you.